Okay, reactions. So first of all, let's just talk a little bit about the function groups that we have. Alcohols, alkyl halides, and alkenes. Okay? And so what we've been talking about in all three of these chapters are, of course, some of the physical properties of them and the stability for these different functional groups, but also how to convert from one to the other and then very significant details of each of those reactions. So alcohols, right, come on. Alkyl halides and alkenes. So what do you know about alcohols? What are the properties of alcohols? Tell me everything you know about an alcohol. I have a terrible oxygen there, don't I?
You start with them in naming.
Okay, you want to talk about naming?
Priority over halogens and double bonds.
Absolutely. So when we name them, using IUPAC rules, we look for the longest chain containing the alcohol. The alcohol gets priority over other things, alkyl groups. Halides don't get priority over alkyl groups. So when we think about numbering and directions and how we find the chains, halogens and alkyl groups are essentially the same. So whatever one is first, you would do. But alcohols will take priority over that. Alcohols take priority over the double bond. Okay, the double bond for alkenes and naming alkenes. We need to name them with the alkene in the longest chain. So keep that in mind. One of the mistakes I see often is people find the longest chain of carbons, but not the one that contains the double bond. Then it's harder to name that as a side chain. So the double bond has to be included in the longest. So even if that's shorter than some other longest carbon chain. For naming, let's see. Remember, with double bonds, we have important aspects of stereochemistry, right? So when you have a double bond, we have 4 different groups on there. Then we have to figure out a way to name it. And if everything is different, then we have to use, we can't just use cis and trans. Cis and trans, same side, opposite side, that refers to groups, identical groups being on the same or opposite sides, right? Or we're referring to 2 specific groups. When all the groups are different, we have to assign priorities. Okay? And instead of cis and trans, what do we use? E and Z. E, opposite sides, right? And Z, same side. That means the highest priority group on either end of the double bond is opposite or the same. So the rules for the priority rules. Who can tell me how we start doing that?
You go by the atomic number of the highest priority.
Highest priority first is atomic number. Exactly. The atomic number. Okay? That's often easy to do just at first glance, right? Because we might be comparing a hydrogen versus some carbon group. Obviously, the carbon's going to be a higher atomic number. Or some halogen. Or something like an oxygen or a bromine or chlorine. Okay? If, as is the case in many examples, we have 2 carbons, then we have to go out further and look for the next, what I look at as layers away, number of bonds away from the carbon of the double bond, okay? So let's just take an example. Let's just draw something here. Okay, how would we do this? Now, we have 2 double bonds in this molecule, okay? One of them, we don't have any issues of cis and trans, because, or E and Z, because this has all hydrogens on it. All right? The other double bond, however, has 4 different groups. On the left side, hydrogen and a CH3, and on the right side, we have 2 different carbon group. So obviously here is the higher priority group on the left side. So which of those two groups gets the higher priority? Okay. You look at it, we have a 3-carbon group on the top and we have a 2-carbon group on the bottom. Is that how we distinguish the priority? No. We go one atom at a time. So if you look at the atoms directly connected, this one is a carbon and this one is a carbon. We can't distinguish that. Okay. How do we consider double bonds or multiple bonds when we just try to assign priority rules?
Count it twice.
Yes, yeah.
So you just lift the bond up?
Lift the bonds up and imagine the atoms they're attached to are going up there. So if you think about this double bond, if you move one bond down here, okay, if you go this way and move the bond here, what was it attached to? A carbon with 2 hydrogens, right? And if you push the bond this way and make a new bond here, it was attached to a CH. That should be enough, and we should be able to consider that. So that's the imaginary group we are looking at when we do this. So if you then look at the groups, so in this top case, we have a carbon attached to 2 hydrogens. So it's carbon attached to a hydrogen, and then another carbon. See that? And in the bottom case, if we're looking here, we have a carbon attached to a hydrogen, a carbon, and then another carbon. Right? There we can make a distinction because 2 hydrogens and 1 carbon. If you can see hydrogen cancels, carbon cancels, so then you compare carbon hydrogen. The carbon has the higher atomic number.
So you can count those 2 double bonds since it's connected to the carbon there. It's
Yeah.
2 carbon-carbon bonds.
Yeah, you think about this as 2 carbon-carbon bonds, exactly.
So that you can count.
Yes. And usually, most of the time you don't have to go any further than that. This one you might not even need to consider at all. Because we made the distinction before even getting out that far. So this, so this carbon, so this group gets the higher priority group. So this is a, what's the stereochemistry? Z. This is a Z alkene at this position, right? Okay. I think we might want to review a lot of reactions. So I want to ask, are there issues with nomenclature that you still have difficulties with? Do you want more examples of naming? Yes, I see some nods. So let's do a few examples. Let's see what I got here.
What if you put an alcohol or something?
If you put an alcohol in there, good question. Let's see if I have an example. I can just write an example here. You mean for doing priority rules and things?
Well, maybe.
Or for naming? Okay. So let's just take an example. I may have a good alcohol example actually. Maybe not. No, I don't. Okay. Let's just take something like this. Okay, how would you name that? So we need the longest chain, ideally containing the alkene and the alcohol. Right? And which gets the priority for numbering? The alcohol. Even though we would overall have lower numbers, if we gave the double bond the priority for numbering, that's not the case. The alcohol needs the lower number. If it were a chlorine or a bromine, then you would go with the double bond. But let's take a look at this. So the longest chain, hopefully, is pretty easy here. We have 1, 2, 3, 4, 5, 6. Okay. So that parent chain is a hexene, right? Hexene. But there's an alcohol, so it's actually a hexenol because the alcohol name comes at the end also. So notice we have basically two endings for two different functional groups in this molecule. So it's a hexenol, but we got to put the numbers on, and we also have an additional methyl group here. Okay, so there's a 4-methyl, a 3-hexenol, and the double bond number would be 4. That's right. You number the double bond from the start of where it goes in the direction of your chain. So there's a number of ways you could do this. You could just say, let's see, you could just say 4-methyl, and probably in this case, you could do it a number of ways. I would probably stick the numbers within the name just to make it clear which numbers go with what. So it would be 4-methyl hex 4 ene 3 all.
Could you put the 4 in front of the hex?
You could, but the big problem would be if you tried to put both of those numbers in front, then you don't know which one goes with what. So at least one of them should be associated with the functional group that you have. And if I'm putting one in, then I usually make it absolutely crystal clear and put them both in. That's my preference.
If you need like 4-methyl, 4-hexene, 3 all.
You could do that, yes. That would be clear on what that structure would be, and that would be correct also. As long as you avoid any cases where you have ambiguous numbers associated with the functional groups. That one would be clear. Okay, but we forgot something. What did we forget in the name of this molecule? And you'll get a point off. E or Z. There's a double bond. It has 4 different groups attached. And so if you look at the left side of the double bond, we have hydrogen versus CH3, right? What's highest priority? On the left side? The methyl, yeah. So let me change colors here. That'll be easiest. This is the highest priority. So on the left side, that's the highest priority. What's the highest priority on the right side? It should be fairly obvious without having to go through too much trouble, right? Here you have a carbon with 3 hydrogens, and here you have a carbon attached to an oxygen, a hydrogen, and a carbon. So the first atom is carbon. The next layer out here is all hydrogens. Here it's an oxygen, a hydrogen, and a carbon. Right? So obviously the group on top is the higher priority group. So this whole group now on that end of the double bond would be the higher priority group. So this is a what? E. That's right. It's an E. So you have to put that E out front. You have to make sure you check the steric chemistry. Okay, let's do some other naming.
For that one?
Yep.
You would put the E or Z depending on alcohol in the methyl group, or between the...
Well, the E and Z and cis and trans usually goes in the very front of the molecule because it's clear that when you're using E, Z, cis, trans, you're talking about the double bond stereochemistry. There's nothing else that could have the E or Z stereochemistry. It's associated with the double bond. So there's nothing ambiguous about putting it there. So it's usually put right in front of the name, in front of everything. Good question. Okay, how about something like... Oh, here's a good one. Oh. How about that? Okay. What's the longest chain? One, two, three, 4, 5, 6, 7, 8. Octene, yeah. Octene. So where would you put the chain? Here? No. The longest chain here, you would include the double bond. So that's 8 carbons, and that's 8 carbons. So you'd use the 8 carbons that encompass most of as much of the functional groups as possible. So the numbering would start here. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So it's not octene. It's octadiene. There are 2 double bonds, so it's octadiene. Octadiene. Okay, that's the parent. The double bonds are on what carbons? 1, 3, yeah. The first double bond starts at carbon 1. The second double bond starts at carbon 3. And notice I can just put those out front because since these 2 functional groups are the same, right, they're both alkenes, the 1 and the 3 refer to alkenes. So there's nothing ambiguous about that. Okay, and then the other group. So we have that chain. Now we have this substituent on the side. How do we name that substituent? There's a common name. Isopropyl. I would certainly accept isopropyl, but the systematic name would be fine too. So you could say, what is it? 3-isopropyl. Okay. What's the systematic name for that complex substituent? Methyl ethyl, but where's the methyl group? Yeah, that's right. In parentheses, okay, let me just put this in green so you can see it. So in parentheses, right, you start numbering from the point of attachment 1, 2, so the methyl group is on 1. So it's a 1-methyl ethyl in parentheses, and that would take the place of isopropyl. That's the IUPAC name, systematic. And now double bond stereochemistry. One of the double bonds, again, doesn't have a stereochemistry. This one doesn't, right? We have a hydrogen here and a hydrogen here. So there's no difference in a hydrogen here. But this double bond has different groups. So we have to put an E and Z. How would you then figure out those priorities? Alkene. So you're looking at alkene versus isopropyl. Okay, let's just look at the alkene group. So an alkene group, so if it's attached to a CH2, that's the group we're looking at, right? That's the attachment. So that's again, swing that down and you have CH2, and here you have CH as the imaginary atoms if you break that double bond. So this is attached to a carbon with a hydrogen, carbon, carbon, all right? So that's that next layer. Isopropyl. Isopropyl group is a carbon here attached to hydrogen, carbon, and carbon. Uh-oh. We can't figure out the priority. So you have to go further. So one of these carbons is attached to more carbons and hydrogens, right? If you will. So if I just took a look at this one, that carbon is attached to 2 hydrogens and a carbon. Wait a minute, where am I at? Yes. This carbon is attached to 2 hydrogens, so from there. Okay, so you see how I did that? In this case, these are just attached to hydrogens. Those are 2 methyl groups. So notice the difference is at this point. That branching in both directions for that double bond actually makes a difference as you go out one layer at a time. When you imagine that double bond being connected to a carbon on either end, that makes a difference. So the double bond actually gets the higher priority. So that would be this group is highest priority, and this group is highest priority on the right side of that double bond. So it is E or Z? Z. Yes, and you'll notice I'm not, in a lot of these cases, I'm not writing in the hydrogen on the double bond very clearly. That's, you have to assume that it's there and in the right position. So be careful about that you don't forget that, where that is pointed. Okay. A double bond has geometry of 120 degrees apart. Even when we draw it flat on paper, okay, you have to assume that the hydrogen not written would be pointed up in this case, or at these 120 degree angles. All right. Okay, maybe just one more. How about that? Cyclic alkene. Okay, we have 2 substituents, a chlorine and a CH3. Some things I didn't draw on here, right? There's a hydrogen here pointing down, and a hydrogen here pointed up. We don't need to worry in a ring this small. You don't need to indicate cis and trans for the double bond. A cyclobutene can't exist with a trans double bond. So that doesn't have to be in the name. So this double bond obviously is a cis double bond, but we would never draw a cis cyclobutene because the trans is impossible. Okay, but we have groups on here, and now we have a ring, and we have the other aspect of stereochemistry, which is groups on the same or opposite sides of the ring. And fortunately, we have 2 of the same groups here, so the hydrogen here and the hydrogen here are trans to each other. One is up and one is down. So the stereochemistry associated with the groups on the ring are trans. Okay. So this molecule has a cyclobutene as the parent name. Cyclobutene. Don't forget the cyclo part. Now we have to number it. How would you number it? Cycloalkenes, where do we usually start numbering? So we number starting the one carbon has to be one of the ends of the double bond. Okay? The double bond gets preference over the other substituents. Unless it's an alcohol, then the alcohol gets preference. I know it's confusing, isn't it? Oh, details. So we have to number one end of the double bond. There's 2 ways we could do this. We could do this numbering. We could do 1, 2, 3, 4. Okay. Or, let me switch colors here and make it easy to see. Or we could start numbering here, 1, but then we have to go in the direction of the double bond. 1, 2, 3, 4. So we can number either way around. That green doesn't show too well, does it? We can number either way around. So how do you think you would do it? What would you say, what would you guess is the correct way to do this? Chlorine first, and for what reason? No. Alphabetical. Atomic number is only for doing the EZ. So for naming this, since chlorine and methyl don't really have priority over each other than alphabetical for naming and numbering, I would go with alphabetical. So I would probably go starting with these green numbers. So this would be 3, I can't use that light green, 3 chloro, 4 methyl, cyclobutene, all one name. Why don't we need to give a number for the double bond? The double bond has to start at 1 for the cycloalkene. Alkene. Huh? No, we don't need E and Z. Oh, sorry, we don't need E. The double bond doesn't matter, but this matters. So in front of this all, we have to have trans, referring to the positions of those groups that are opposite.
So E and Z sometimes aren't completely interchangeable.
No, they're not. They're not. E and Z we would never use for groups on the top or bottom of a ring. We would only use that for double bonds. Okay, I think. Oops. Sorry.
Like just general, like when you advertise them, for this one, does it go because of chloral and methyl?
Yes.
Or is it the actual?
Chloro, it's the alphabetizing order of the substituents. So yeah, C before N. Right. This one should be pretty simple. Let's see.
So even if that would have been ethyl, we would have done the chloral first.
C before E, yes.
They also have the same priorities.
Yeah. Yeah, don't confuse priority for the EZ figuring out highest priority by atomic number to priority of ordering of numbers, ordering of a numbering on the chain. Here's another cyclic alkene. It actually happens to be a diene, cyclo, what? Cyclo, how many carbons? Hexadiene, right? Cyclohexadiene. Okay. We have one substituent, which is a methyl group, and what numbered carbon would it be? 2. You're right. We have to start numbering at the end of a double bond to give the lowest numbers. And now in this case, we have 2 double bonds, so we would number in this direction. So it's a 2-methyl. Okay. In this case, there's more than one possibility for positions of double bonds in the ring, relative to each other. So here, we need to put 1,3-cyclohexadiene because the other possibility would be a 1,4-cyclohexadiene, which would be a different molecule. So if I had 1,4-cyclohexadiene, sorry, it's not the best hexagon. Okay, 1, 2, 3, 4, 5, 6. That's a different constitutional isomer because the double bond's in a different place. Double bonds and hydrogens have moved around in this molecule. So when you have positions of groups that are ambiguous, or there could be other possible isomers, then you have to really indicate numbers. Okay, so this would be a 1,4-cyclohexadiene. That's in it. Because the double bonds start on 1 and 4. All right, any other questions on naming?
With this, are you indicating the stereochemistry?
What stereochemistry? Of the double bonds?
Yes.
You don't have to with a ring because there's no way you can have a trans double bond in these rings. And frankly, I won't be giving you rings that are 10-membered rings or larger. That's really the only ones that can accommodate trans double bonds. All right. All right, let's talk about those functional groups again. Alcohols, alkyl halides, and alkenes. We have ways to make them. So we have ways to make alcohol. So let's just talk about alcohols for a moment. If you wanted to make an alcohol, I put R, but it could be any kind of carbon group. We'll look at some specific examples. But if you wanted to make an alcohol, what kind of reactions do you know to make alcohols? From chapter 4, 5, and 6, we've been focused on these three functional groups, alcohols, halides, and alkenes, and their interconversions. So if you look at an alkyl halide, have we talked about ways to make an alkyl halide into an alcohol? Okay, you've studied the reactions, right? Test is tomorrow. Any way to make an alkyl halide into an alcohol that we've talked about so far? No. Alkene to alcohol? Yes. Okay. We know that we could take an alkene and convert it into an alcohol. And there are a couple of ways to do that. We could make it into this alcohol, or we could make it into this alcohol. And we can do that very selectively. Okay, so someone asked, give me examples of reactions where you have to provide the reaction conditions. So someone give me the reaction conditions. The reagents you need to accomplish these reactions. For which one?
For the top one.
Yes. That would work. H3PO4 in water. Okay. Water is important, right? Because it's a hydration reaction. We're adding water under acid-catalyzed conditions. You could use other acids. You could use sulfuric acid, H2SO4. In this case, if you simply said H3O plus, indicating that it's an acid catalyst, I would even accept that, because because the rest of the acid in aqueous conditions may not even matter that much. Okay, how do you do the second one? Anti-carbon addition, right? So it's not going by the usual way. We're getting the alcohol on the less substituted carbon, and the hydrogen goes to the more substituted carbon. And to do that hydration, not directly, we need to use a surrogate for the OH group, right? And what is that? A hydroboration, yes. So you need to use borane, BH3, or, and I'm not going to worry about the solvents and everything in this case, so don't worry about that. B2H6 would be a dimer of that borane, so either way, BH3. And that's followed up, though. It's very important because that puts a boron on. It doesn't make it into the alcohol. We need a second step to make the boron into an alcohol. What are those reagents? Hydrogen peroxide, yes. H2O2. And it must be done under alkaline or basic conditions. So sodium hydroxide, or I just write OH minus. Okay. Good. So hydration of alkenes, and these go by two very different mechanisms. But the concept is the same. We have a double bond. We add something plus to it, or quote plus, and that ends up on the less substituted side, leaving the carbocation, or if you think about that Markovnikov addition, the water adds to the middle. That's happening in the first case. So in terms of reaction mechanisms, you should remember, obviously hydration. You don't need to know details of hydroboration if you know the product. But if you generalize what you think about as plus minus, then it helps a lot. SN1, SN2, E1, E2, elimination, substitutions, and we're going to cover some of the details of that tonight. So, protonation in this case gives you a proton on the end and a carbocation, and it does that because it is more stable than the alternative. Right? That's the lowest energy carbocation, and then water adds to that. Sorry, I'm running out of room here. Terrible. Okay, you get that water add, and then water will... Actually, I should do this in a whole... I'm going to repeat all this. Hold on. Do this sequentially. Okay. This gives the most stable carbocation. Okay. In the presence of water, we generate this, and then make it clear here. I want to use the same colors. Okay, so does every step of this make sense? And would you be able to draw all of these reaction arrows and know what they mean? Okay? Alkene protonated carbocation, you generate the most stable one. The nucleophile in this case is water. It adds that carbocation. Now water has 2 hydrogens on it, so the initial intermediate is OH2 plus, right? Formal plus charge. And then you have to lose that hydrogen or the proton back to the acid catalyst that it came from. Okay? If you wanted to make an alkene, it's the exact opposite of this. Right? The forward reaction here, alkene to alcohol, is a hydration. The elimination reaction is a dehydration. Okay, so the elimination reaction would go in this direction. And use a strong acid. I'm going to specifically say sulfuric acid, if you will, because you protonate that alcohol, you would go back to that intermediate. You lose the water, right? Notice if you go in the up direction, we've lost a molecule of water. I just write minus H2O. If you're going down in the forward direction, we're adding that molecule of water. So see how those steps are exactly the same but opposite, right? So carbocation and loss then of the proton, that's the elimination step. That forms the double bond. So backwards you go. Notice every step in this process is reversible. So why would it go one way or the other? Yeah. How much water you have. If you have it just under concentrated acid conditions, right, this is going to go this direction, the green direction. If you have it under aqueous conditions with acid catalyst, you're going to go in the blue direction. Question?
That hydrogen wasn't there on the top right. Wouldn't the major product be the double bond on the second carbon?
You're absolutely right. I drew the wrong product because the elimination actually has the possibility of forming 2 products. So notice there are hydrogens here as well. So if I do the elimination reaction, I actually don't get back to where I started with to make this alcohol, because the major pathway would be taking one of these off. Okay, and you'd get that. Why would you get that one?
More substituted.
It's more substituted, meaning it's a more stable alkene. Okay, I also drew the trans. This will be the major product. Okay. This would be, if it's formed, this would be very minor. There's another minor product, and that would be the cis product. So in elimination reactions, you form the more stable alkene. Question?
Just to clarify, what does it say up in the top corner?
HSO3 minus. So if I just, that's the conjugate base of sulfuric acid. I just use that to illustrate you generate that acid catalyst back. Okay. Essentially the A minus.
So that HSO3 is just your nucleophile.
Sure. Yep. Yep. So that actually these two reactions were discussed in two different chapters, but they are intricately related. So some of the details you would need to know, which was pointed out that, well, yes, there's more than one way you could eliminate. So if you take that double bond, by the way, and you simply treat it with an acid catalyst without water present, you can actually isomerize it. It can protonate to form the carbocation, but if there's nothing to add to it, it'll just eliminate back. But then it can allows elimination in a bunch of different ways. Okay, alcohol. So alcohols by hydration. Acid catalyzed hydration goes through a carbocation intermediate. And remember the general rule, if you're doing anything with acid, if it's under acidic conditions, you're not going to have negatively charged carbon species. You're going to have carbocations being formed most of the time. I was going to say something else about this. What was I going to say? I don't remember. Hydroboration reaction. There are some details to remember, and you don't need to know the details of the mechanism, but just if you do remember that hydroboration will react in a one-step process at the same time, and that could be two hydrogens or whatever. Okay? This reaction is controlled, two aspects of the reaction is controlled using this. One is what I've shown here, the boron adds to the less substituted side. That's why when you convert that to alcohol, it looks like an anti-Markovnikov addition of water. Okay. So BH3 will always add to get boron to the less substituted side, and then our peroxide under basic conditions will give us the alcohol on the least substituted carbon. Okay? The other aspect of this reaction that's important, because hydrogen and the boron are adding at the same time, how would that have consequences in, say, cyclohexene? Well, let's take a look. Let's say we take this molecule. Okay? I take 2-methyl or 1-methyl cyclohexene, treat this with borane and then hydrogen peroxide under basic conditions. What's the product? Okay. The boron and hydrogen add across the double bond. Boron will add on the less substituted side, less substituted end of the double bond. And then we convert the boron to an OH. Okay. But since we've added boron and hydrogen at the same time, they have to be on the same side. Syn addition, right? It's a syn addition of the boron and the hydrogen. So the intermediate, let me just say boron comes from the top of that double bond. So the initial intermediate would be this, with the hydrogen up. They have to add on the same side, and the methyl group down. Now keep in mind that that could equally come from the bottom, right? But still the hydrogen and boron are on the same side. I'm just drawing one of the possibilities here. So the product, in the end, has the OH group, that's the second step, has the OH group up, that's where the boron was, and if I don't write the hydrogen, it's still there, but we don't write them in these structures. The CH3, oh, I'm running out. Uh-oh, it didn't show up. There it is. And the CH3 group is down. I'm sorry. Yeah, CH3 group is down because the hydrogen's up. Okay, so if you have a cyclic structure and you do this reaction, you need to know that that happens to be from the same side and that affects the stereochemistry. Okay. Question?
If the double bond is on the methyl group, so it goes like the methylene,
Yep.
the boron would go.
Yeah, so if you take a look at this molecule, like that, and we carry out that same set of reactions, what's the product? Someone tell me the product. And what would you have to write? Yep, good. You remembered methylene. And the hydrogen. Yep. So I would write this like that. That's the product. Okay. I know a lot of you would probably write this, and there's nothing wrong with it. Let's see. I do this. Okay. Why did I write it like that? Well, because you remember they come from the same side. But this doesn't mean anything. These bold and dashed lines don't really mean anything. Because we're not doing a reaction of a double bond in a ring. There's no cis or trans. Notice these are two hydrogens. It doesn't matter. This is free rotation. This hydrogen is not relative to anything else around the ring. So there's no need to actually show any stereochemistry because it doesn't mean anything if there's nothing else relative to it. But I guarantee a lot of people would write that because they remember it's in the cis and they'll show bold and dash. And I wouldn't mark it wrong, but it looks odd when it's not needed. Yes?
So syn addition is for hydrogenation and
yes.
this.
Right. This adds on the same side of the ring, or same side of the double bond. If the double bond doesn't, if the double bond is not within a ring, and there's not different groups, you don't see it as cis and trans. But it is happening syn addition for this, and it's also happening. So if I go back to this example, well, let me give this example. That'll help. Right, that's another reaction we can do on double bonds is hydrogenation. H2, let's say with a platinum catalyst. Right? If you ever see these metals and hydrogen, you know that's a hydrogenation. It's the two hydrogens adding. Don't draw metals connected to the carbons or anything. In this case, this also goes by a syn addition. Two hydrogens will add, and since I do have two groups where it's adding, it will. You have to indicate the stereochemistry. Let me just erase this. So the product here would be addition of the hydrogen, but you would have to show. So for example, if the hydrogen came from the top, as I've shown it here, the CH3 groups would be down. Okay. Two hydrogens, I'll show them for clarity here. Two hydrogens are both up, or you could draw them both down. Either way, it doesn't matter. As long as they're both on the same side when you draw it. That's important. Okay. What reaction reacts with the double bond in an anti-fashion? Huh? Anti-addition, right. What reacts that way? Br2. Yeah, Br2 or Cl2. I haven't really shown much examples of Cl2. let's just take a simple case. Okay. React that with Cl2. What do you get? You get a chlorine adding on either side of the ring. One of them is up, and one of them is down. Anti-addition. Okay, so the chlorines end up trans to each other on that ring. Selectively. And why does that happen? The carbocation is not formed. What's formed when we have anything bigger than a proton like this, whenever we have a halogen, we form the double bond reacting to form the halogen in a three-membered ring. So if I look sideways on this, I'm drawing it flat. It's not really flat, but you get the idea. If I look sideways on this, that's in a three-membered ring. So the first step breaks one of the chlorine-chlorine bond. And because that bond to the chlorine is both on the same side in that intermediate, this one can only add and push that up from the bottom in the way I've drawn it. So it has to be opposite. So this chlorine bond that remains here is on the top side. The new chlorine bond that's forming from the other chlorine is opposite that. Okay? And if I do this reaction with chlorine in the presence of water, I don't get the dichloride product. What do I get? Yes. Chlorine plus adds, you get the same intermediate because it's the chlorine Cl2, a source of Cl plus, which is the electrophile. And then instead of chlorine here, we have water. So water instead of chlorine will do this addition. So instead of chlorine down, this will be replaced with OH. Okay. Yes?
So is that other chlorine picked up by the hydrogen, or that takes out the hydrogen?
Yeah, so the byproduct here would be HCl, correct. The byproduct's HCl. So this actually gets into some of the gray areas of chemistry, right? So we have, in this case, the reactant with electrons that's reacting and giving its electrons, chloride or water. That's in that second step. That's the nucleophile. This is a matter of which of those is a better competing nucleophile. And we haven't really talked about details. I think that comes in Chapter 8. We'll talk a lot about different types of nucleophiles and their relative comparisons. But clearly, if you do this reaction, water is out-competing chloride as a nucleophile. It's a better nucleophile in this case. Let's see. There's another aspect to this reaction. Even though you don't form a carbocation, okay, let me take this. Okay. If I take that reaction, what's the product? We have Br plus, and it forms a bromonium three-membered ring. In this case, the double bond's not in a ring, so you don't really tell in the product whether it's anti or syn from the product stereochemistry because there is no difference. But it still is an anti-addition. But there's also an issue of selectivity, right? Which position the bromine's on and which position the OH is on. So where does the bromine go? So we have the element. So if you remember that chart that I tried to generalize things that are plus and things that are minus in electrophilic additions, we have, you know, A plus and B minus, and where does it go? And so in this reaction, what's adding first to the double bond? That's going to be what we consider the plus group. So what's adding first? Bromine or water? What's adding first to the double bond? Bromine. In this case, bromine, this Br-Br bond, it's a Br plus, which is the electrophile, right? So this is reacting first. So this is the first group. That's the plus group, right? And that always adds, if we think about our generality of Markovnikov addition, if it's H plus, if it's Br plus, or if it's electrophilic boron, BH3, that's going to add to form the more stable carbocation, although the mechanisms change a little bit. But you can use the same principle if you want to remember that to guide you. The plus group adds to the less substituted side. The second group is going to be water. That's what our B minus is here. That's going to add to the more substituted side. So the product will be OH on that carbon and bromine on the N carbon. Okay, it's selected. So if you remember those generalities, it doesn't really explain the mechanism explicitly, but it helps guide you as a pneumatic memory tool to tell you which side it goes on. Yeah, question?
So, like, could a hydride shift occur?
So yeah, I was going to get to that next. In this example, you wouldn't see a hydride shift. Bromoniums, because it's not a carbocation, that's the intermediate, okay? The difference is, though, this carbon is more substituted, so this bond is actually longer and there's more partially positive charge, but it's not a free carbocation. This is why the water then adds to that carbon, but you don't form a free carbocation. In general, we don't see rearrangements with bromoniums. However, we do see them when we have protons. But if you just look at this example, let me just erase that bromonium. If we do have a free carbocation, let's say we reacted this with sulfuric acid in water, okay? That protonation would occur to give that hydrogen adding to the end and a plus charge there. Would that undergo rearrangement? Would you expect that to undergo rearrangement? What's the driving force for carbocation rearrangements? Yeah. From a less stable carbocation, it would form a more stable carbocation. So if you're going to rearrange or shift a hydride or a carbon group over, you have to be forming a more stable carbocation. So notice, this is a secondary carbocation. Next to it, if I look at it, there's two hydrogens there. If that shifts over, okay, what kind of intermediate would we have? Okay, so that hydrogen shifted over, so the plus charge is here. Right? And that hydrogen ended up here. That's a secondary carbocation. Notice in the example I chose here, if you form a carbocation, it'll react with water before it rearranges, because this rearrangement isn't going to be fast if you haven't gone down in energy. It's the same energy. However, if this methyl group were one more over, or let's see, if I were to, maybe a better way to do it is get rid of all this junk here. Let's say instead of this double bond, I started with this double bond. Okay, notice the difference. If I protonate that with an acid, that hydrogen added to the end here, that leaves a secondary carbocation. Now, let's say I have a hydrogen on that carbon next to it. If I shift that hydrogen over with its electrons, now I get something that's more stable. Okay? Okay, so that hydrogen ended up there. That leaves now a tertiary carbocation. That will undergo rearrangement because we've gone downhill in energy. Okay? So this one probably wouldn't happen because it's the same energy and it would react with the water faster. This one, because it goes downhill in energy, that rearrangement will be faster than the water adds, so it'll rearrange first and then the water will add. Yes?
So that hydrogen, the green one that you drew, was on that.
Yeah.
The tertiary, that one on that.
Yeah, so yeah, that's the one that moved over. So notice there's a lot of hydrogens I'm not drawing here, but I'm just indicating. This one was here to begin with. It moved with its pair of electrons, right? That's the important. Moved with its pair of electrons.
See if we can just do the level of the
Yes. Let me just show an example of that. Okay. You can add things besides hydration also, by the way, or bromonium, Br2 or Cl2. You could add something like HCl. Okay. This makes an alkyl halide through a carbocation. So if I were to do this, how do you think, actually, let me just say, if you were to see this reaction, which you're seeing for the first time, what products would you predict could result from this? Or adding H plus and then Cl minus. Okay. Add H plus to the double bond. What are the possible intermediates? You could react this double bond with H plus. There are two different carbocations you could generate. If the hydrogen added to this end, okay, notice there's already a hydrogen on there. That gives you this carbocation. Okay, that's possible, right? That's a secondary carbocation. There are hydrogens here. Obviously, one of them came from the proton, one was already there. So two hydrogens here, there are two hydrogens here. If you were to shift any one of those, it wouldn't be lower in energy. So not much will happen there. That secondary carbocation then will react with the chloride. Okay. So one product you could get would be this. Right? You added H plus on one end of the double bond, Cl minus on the other. Notice that double bond is the same substitution on either side. So initially, before you form any carbocations, there's no difference between those two carbons. It has a carbon here and a carbon there. This case would be a complicated one because this will be a product, but you'll also have another product. Okay. If you added the H to this side, that leaves a plus charge here. Okay. That could be another carbocation. That's also a secondary carbocation. Notice those two carbocations are both secondary carbocations. But this is an interesting one because this one has a possibility to rearrange. And it will rearrange potentially to move this CH3 group here, I'll draw it out, with its electrons to shift over. Sorry, is that too small? Can you see that? That'll shift over. Okay. That'll put that CH3 group there. The other CH3 group is here, and the plus charge that's left because the electron's left from that carbon. That's now a tertiary. Secondary carbocation to a tertiary carbocation. That would happen. You go downhill. So if you were, let's say the question asked, starting with this starting material, how many different products could you make by addition of HCl? This is one of them down on the bottom. If Cl minus added to this, faster than rearrangement, you could potentially get this product. Or if Cl minus adds to this one, sorry. Can you read that scrawl? You would get that product. Cl, methyl, methyl. Carbon rearranged. Let me draw that a little more clear here. That's more clear, yeah. So there are actually 3 possible products. Most likely this one would be a major one and this one would be a major one. That rearrangement would happen pretty fast. A lot of things to remember, right? The more you see it, hopefully the more it makes connections, yeah?
Wouldn't that first one be less common? It's a slow reaction.
Would be what?
To rearrange, it's a slow reaction, so it needs less.
Well, no, this rearrangement would be fast. By the way, if you think about this process, let's just think about, I gotta erase everything to make room. If you think about this first protonation would go up in energy, right? And you get to this intermediate, and then you go lower in energy to do the rearrangement. And so that if that's downhill in energy, it's going to happen pretty fast. And then you go down to the product of energy. Okay? So because it goes from a secondary carbocation to a more stable tertiary carbocation, there's a driving force for that. And it happens pretty fast. Okay, let's see. Any other questions on electrophilic addition of like HCl, hydration, addition of bromine or chlorine or iodine? We've talked about, we didn't talk about substitution yet. There are several types of substitution reactions. Along this same theme of carbocations, of course, is the reaction of alcohols with hydrogen halides to substitute the OH group for the halogen, right? That's a reaction we know will undergo the reaction by the mechanism that was similar. It's kind of a, if you look at that hydration and elimination from double bond to alcohol, this is a different pathway off of that if you have hydrogen halide, no water. Produces water, but we don't have a lot of water to begin with. So how does this reaction work? Protonation of the OH group, right? Now notice that becomes an intermediate that we've seen before. Okay. Loss of the water, minus H2O, to form, I'm being really generic here, to form a carbocation, and then our X minus will add to that carbocation to form the halide. Okay. If there are hydrogens adjacent to the carbocation, you can eliminate to form a double bond. We talked about elimination. That would be a pathway, eliminate, to form alkene. Okay, and so you can see how all these things are related. These same intermediates, protonated water, carbocation, depending on what we have there, it goes different ways. So, all of the same things we've just been talking about with regards to carbocation stability, ability to rearrange. We form a carbocation that can also undergo rearrangement. You don't have to start from a double bond to make a carbocation, rearrange it, then add chloride. You can start from an alcohol, make a carbocation, rearrange it, add a chloride, or not rearrange it. So all those chemistry we've been talking about, doesn't matter how you generated the carbocation, the nature of the carbocation is still the same, right? If it's secondary and it could rearrange to a tertiary, it will. If it's a tertiary carbocation, it's going to be faster formed. The substitution reaction depends on this step as the slowest step, right, which only involves water coming off. That's the SN1 substitution. Okay. So forming carbocations under this method from alcohol, protonate, loss of water, happens with what kinds of substrates, what kinds of alcohols? In terms of substitution. Tertiary and secondary. Okay, tertiary and secondary alcohols. Those can form carbocations easily enough that it will occur. A primary alcohol won't. Okay, so let me give you a specific example. This will react quite readily, probably at room temperature, to replace OH for Br, right? Why? Because you first protonate okay. That alcohol is attached to a tertiary carbon. Formation of the carbocation by loss of the water is quite easy. It's a nice stable tertiary carbocation. Nothing to rearrange to be more stable, so we don't have to worry about that. And the bromide generated in that first step will add to the carbocation and give that product. Okay. If it were just cyclohexanol without that other methyl group, it'd be a secondary alcohol that would do the same thing. You can form secondary carbocations without too much of a problem. If I had, let's just say, that alcohol, you will convert that alcohol to the bromide under those reaction conditions. The product will be the bromide, but the mechanism is slightly different, right? How does the mechanism change?
Bromide is added as the water is kicked off.
Exactly. We still protonate. Okay, we get an intermediate with the OH group protonated. OH2 plus. But a primary carbon won't form a carbocation. That is really high in energy, and it will avoid that at all costs. And so to get here, the bond making happens at the same time as the bond breaking. And that's an SN2 mechanism. Okay. Substitution nucleophilic bimolecular because it takes both the bromine and the substrate, alcohol substrate, in the slow step, which is that one. Okay. So the difference is, of course, everything comes down to stability of the carbocation. If you can't make a stable carbocation or a stable enough carbocation, you're not going to form it. If you can avoid carbocations at all costs, actually it's best. But So SN1, substitution nucleophilic unimolecular, because notice this slow step here only depends on the alcohol substrate. Yes, it's been protonated, but the alcohol substrate breaking the bond, the bromide is not involved in that step, so it's just one molecule breaking apart. This requires two molecules breaking apart, SN2. Another way to keep things straight in your mind is whenever you have a 1 unimolecular, we're talking about carbocations. So SN1 and E1 carbocations. SN2, no carbocation, nucleophile kicks off the leaving group. But now let's talk about E2 elimination. Because that has some features of it that are very important to remember. In an elimination reaction where you don't form a carbocation, there's a very specific geometrical requirement. So whether you're eliminating a water group or you're eliminating a halide, which we talked about most when talking about E2, because they really work well. Like a bromine, for example. The elimination has to occur in a very specific orientation, right? And these reactions usually require a good, strong base to grab the proton at the same time the double bond forms, kicking off the leaving group. Okay. So no carbocation formed, just elimination by taking the proton off so the electrons can go down and push the bromine off, or whatever leaving group we're talking about. So this has to be anti-periplanar, or what does your book use the term? Coplanar? No. Anti-coplanar. Those have to be 180 degrees apart in an anti-configuration in order for that to proceed. So if you look down the Newman projection and see from the front carbon here to the back, 180 degrees apart. Okay, and on adjacent carbons. Because some molecules are very restricted in how they can rotate, there are cases where it's important to know this. If it's just an alkane with no rings, it doesn't matter because single bond rotations, you can always align it to do the elimination. But if you have cyclohexanes, right, that requires a very specific alignment, but you only have so many choices. I'll just tell you one way to remember easily this cyclohexane, because you noticed if you've looked at the old tests and what we've talked about in class, it's a question I'll always ask about, and you should know that. A cyclohexane, let's just draw it flat. Regardless of anything else, if you don't remember anything else, if you have a leaving group, such as a bromine, on a cyclohexane, and it has to eliminate, the only way it can eliminate is if there's a hydrogen adjacent and trans to it. So the carbon next to it has two hydrogens, okay? Well, if I just look at this case, and the carbon there has a hydrogen. One of them is on the same side of the ring as the bromine. One of them is on the opposite side of the ring as the bromine. Only the one on the opposite side of the ring, only a hydrogen trans to the leaving group, can adopt an anti-periplanar alignment, right? Obviously, if it's on the same side of the ring, it could never be opposite. It could never be 180. So you should immediately exclude, you know, things like this. Those can't participate in the elimination, only those. Okay? So you can remember that actually, even just looking at this flat, you should be able to say, if I gave you an example like, Okay. Will that undergo elimination? Can you do an elimination? No. You don't even need to think about, in this case, the chair conformation, in which case an elimination always has to have the leaving group axial and the hydrogen axial. That doesn't even matter because here, opposite the bromine is a carbon, there's no hydrogen. Opposite the bromine is a carbon, there's no hydrogen. It doesn't matter which ring conformation you have. None of them could have a hydrogen antiperiplanar. If I took something like, let me just change this here. Let's just say this. Okay, that could eliminate, right? That one has a hydrogen down, trans to the bromine. This hydrogen is trans to the bromine. That could undergo elimination. Now, the question would be, is it fast or slow? That's where you would really need to think about what is the most stable conformation. So what do you think? Can you think about that in the three-dimensional picture? Yes, no?
Only if the bromine is axial.
That's right. The bromine has to be axial. Let me just erase this one here for a minute, make some room. The bromine has to be axial, and if you consider both of the conformations, well, let's just draw one. And the way to do this is it doesn't matter which one you start with. You draw one, and you put the groups on, and then you look at the opposite. Or just draw one, and then think about each position changing. So let me just draw a chair. Let me just start here. Okay, CH3 up. Okay, and then I'll come closer to me. That means the hydrogen is here. Here's two positions. Bromine is up, and hydrogen is down. Okay, oops, not H3. Hydrogen is down. Then the CH3 group is, let's see, there's an up position and a down position. CH3 is down. Hydrogen is up. Okay, notice the CH3 is axial, the bromine is equatorial, the other CH3 is equatorial, right? Can it eliminate like this? No, can it eliminate from this conformation? No. If it has to eliminate, it has to flip. Because this bromine needs to be axial, and that hydrogen also needs to be axial. Bromine, if you flip this, the bromine will be axial up, the hydrogen will be axial down. Okay. But, of course, then everything flips. So in this case, we have one axial methyl, equatorial bromine, equatorial methyl. If you flip everything, you have axial bromine, axial methyl, equatorial methyl. So you have more groups axial in the conformation required for elimination. So which one would be harder to do? Well, the conformation needed for this to eliminate is higher energy. So it would take more energy or it would be slower. But it could be done. Could be done. And only in one direction. Right? Only the hydrogen there cannot be eliminated. Okay. Let's see, any questions about that? About the E2 elimination? In general, E2 elimination is best done with elimination of hydrogen halide. So it's the opposite of addition of the hydrogen halide to a double bond. And requires strong base. What other reactions have we had? We talked about a couple other ways to make halides, right? So to make alkyl halides, we can take a double bond plus HX, and we can add across the double bond and add HX, right? That's acid catalyzed, and that is going through a carbocation intermediate. Okay. So, oh, sorry. Yeah, that's one way to do it. Stop it. Another way to do this is to start with an alcohol, right? HX will give an plus water. Okay. That goes through a carbocation if, right? Carbocation if it's secondary or tertiary. Okay. Or it goes through an SN2 if it's a primary alcohol. Okay. But still under acid conditions. HX is still a strong acid. We can go directly and more selectively and by using another way, right? We could use SOCl2 in the presence of a base, a mild base like pyridine. Important thing to remember is SOCl2. The pyridine doesn't do anything except absorb HCl. That works. We can convert OH directly to the halogen. Okay. This reaction goes by what mechanism? Someone who whispered it. Come on, be more bold. You know what you're talking about. SN2. Yes, this is an SN2 process. It's just a different way to make the OH into a good leaving group so chloride can kick it off. So it will only work best with primary. Actually, I will qualify that. These, since we're not under strong acidic conditions, it could also work with secondary, but not tertiary. If we wanted to make the bromide, we could use SOBr2, but practically in the laboratory it's a pain because it's very hard to handle. So we use something else instead to make the bromide. Also an SN2 reaction. Remember what that reagent is? Phosphorus tribromide. So those were just two other ways in which we have to make halogens, whether we selectively want to make the chlorine or the bromine. Just want to make sure I haven't missed anything else. Hydroboration, hydrogenation, addition of HBr, bromoniums, free radical halogenation. Okay, that's a substitution reaction. But under a very different kind of mechanism, okay? How does this happen? Breaking.
Cleavage.
Yep. Initiation, this is a free radical reaction, so we usually describe this in terms of the types of elementary radical chain mechanism steps. So in initiation, you supply energy in the form of heat or light to break the bond into two bromine radicals. Okay, one electron each. Because alkanes don't react with much of anything except things that are really highly reactive. Propagation, one of those bromine radicals will react with, in this case I've chosen cyclopentane. Let me just draw here the hydrogen. Okay. That will pull off a hydrogen. To form a carbon radical. And the carbon radical will react with bromine to continue the chain and provide the product. Okay, so those propagation steps all result in propagating some reactive free radical species, but those are the elementary steps involved. Initiation to make radicals, radical exchanging with other atoms, hydrogen or bromine, depending on the particular step. Generating still something to carry on and be reactive. If any of these radicals involved combine, if you take two bromine radicals, combine them together, and you go back, that'd be a termination step. If you took a cyclopentyl radical or any carbon radical plus a bromine radical and make the product, it doesn't produce anything to further the chain, that's a termination step. You could even, if these are made in high enough concentration, combine this with another molecule of itself. But if it doesn't form another radical, then it's a termination step. Okay. Free radical halogenation. So if you do this kind of reaction, what does it work best with? If you wanted to do this practically to synthesize a material cleanly and make one isomer, you can do it on a starting material that has all the hydrogens equivalent. Okay? If you have different kinds of hydrogens, like you have different substitution and it's not a symmetric molecule, you're going to get a mixture of products. So, butane will give you two different products, right? With a bromine on the end, a bromine on one of the middle carbons. The more complicated your molecule is, the more possible products you can make, because any of those CH groups could potentially come off. Some more preferentially than another, because what do you know about the stability of radicals on a carbon? Yep, just like carbocations. The more substituted, the more stable. So you'll preferentially form those if possible. Okay. Have we covered everything? Do you have any more questions or about anything specific? Problems you want me to do? Yep.
Are you able to go over the mechanism for the alcohol with the pyridine and the SOCO2? Or do we not need to know?
You won't need to draw it or know it. I'm not going to ask you that mechanism, but it's you want to see it, I can show it to you. Yes?
Practice test, we don't have to do anything with the polymers.
No, we didn't cover that until Wednesday. I'm not going to include that on this test. So anything up through 617. Yeah. Well, there's my test from last year. The problem is it's mixed. There's some chapters that are mixed up. So if you go to my old web page, then all my old exams are there for the whole. So I presume that's when you're looking at, right? 2007. Yeah. So the book that we used then presented material in a kind of a different order, and so there were some different reactions and some reactions that we've talked about that weren't there. So some of the reactions aren't quite the same. Yes?
How do you determine the substituents you use to name the molecule E or C? Like if you have multiple alkenes,
Right.
in the molecule,
Do you have a specific example you'd like to go through, or?
or you went through all of them,
Mm-hmm.
and just confused why you use that. So you use C versus other carbon.
I'm not sure I quite understand your confusion. I'll do one more if you want.
4-methyl-4-hexanediol.
Yep.
You use the center one for the E.
E234.
Yeah, and then like you have that other alkene right there. 2 alkene. Like why do you use parts for carbon number 3 versus number 2 to determine whether it's E or Z?
So yeah, be clear about this. When you're looking at E or Z, the double bond we're looking at, maybe if I draw this a little different way, I'm looking at this double bond here, okay? If I draw it all out, maybe it might be a little bit easier. If I draw it this way, does it make it a little bit more clear about how I did that? Because what I'm looking at is there's only one double bond here, and you'll notice if I look at this and split it in half, this group is different than this group, which is different than this group, which is different than that group. Okay? And so what I have to do is look at the left side of the double bond, because I got to compare something on one end of the double bond to the other end of the double bond. Oh, wait. I see what you're saying. Why did I call that E? As opposed to...
well, like, let's say you put another double bond in there, so it would be a diene.
Yep, like this.
Like, how do you know which one to use when you're going to name it Z or E?
Okay. The dienes I gave you, I did something probably like this. Okay. Okay, maybe something like that, right? Only one of them has the possibility for different stereoisomers. The other one has no E or Z. So notice, this has hydrogen, this has hydrogen, this has hydrogen on the ends of the double bond. So if I switched the hydrogen and this hydrogen, would it be a different molecule? No, because those are the same. Okay, so there is no stereochemistry associated with this double bond because there's nothing different on both sides. Okay, this is the only one which has different groups. These two groups are different, these two groups are different, so if you switch these two, it'd be a different molecule. Okay, or if you switch those two, it'd be that other molecule. So when I have more than one double bond, only one of them has the issue of possibility of two different isomers. So that's the one that we're referring to. Okay, it is possible to have molecules where both double bonds or even more than one double bond could have the different isomers. And then you would have like those you could have E comma E or E comma Z, 1, 3, diene, whatever. That's possible, but I'm not going to give you anything that complicated. You might have more than one double bond, but only one will have stereochemistry. Okay? Last chance. Questions? Yes?
Will the format of this test be similar to that of the last one?
Yeah. Yes?
Should we know the regulating steps and thermodynamic graphs for reactions?
Yeah, so I didn't really go through a lot of this, but you should have a good sense when we talk about SN1, or let's just say the elimination, not the elimination, the addition of HCl to a double bond. You know it forms a carbocation. You should have an idea about what that energy profile might look like, what should be the slowest step. Substitution, SN1, carbocations, yeah, definitely. So the ones that we've really focused on for mechanisms, you should have an idea about that. SN1, SN2, E1, E2. Remember, the 2s are usually this one step. 1s, carbocations, that's the ones that we've been focusing a lot on. Carbocation, carbocation, carbocation. Okay? All right. We'll see you tomorrow.